finally, today we'll hear from Shlomit Beker. She's a postdoctoral fellow in the lab, and she's going to talk about some of our hot off the EEG data today.
Thank you. Thank you, Sophie, and thank you for staying for the last talk. So, my name is Shlomit Beker, and I'm a postdoc here in Einstein, working with Sophie and John. And today I want to talk about anticipation and impaired anticipation in children with autism. So, when we look at this cartoon, we can predict the next move. We can almost hear the puff coming out from this guy. So then when we actually see it, we're not surprised because our predictions are validated. Prediction of incoming sensory inputs is thought to play a significant role in perception and cognition. To navigate the world, we use cues that allow us to prepare for upcoming events, and we adjust our expectations to suit the environment. However, what if not all the people use cues in the same efficiency? And we have the reason to believe now that maybe this is the case for individuals and especially children with autism. So before I'll show you some results, the clinical context is as follows. Literature has suggested that individuals with autism are less inclined to use cues efficiently. They do react to sensory information, but they're not really preparing for it properly. They show impairment in applying predictive information to generate expectations, and they also are more surprised when predictable stimulus occur. Being widely documented and reported by clinicians, this rigidity, insistence on sameness, and lack of flexibility is in the diagnostic criteria in the DSM. There are abundant of studies so far that show lack of the ability to predict and to adapt. However, the majority of these studies are based on opinion pieces, on reviews, and on clinical data. And this is where we enter. We want to test the ability of individuals with autism to use cues properly in order to anticipate upcoming target events. We want to find a neural correlate. We want to see how well their brain can track those cues. And also, we want to find an early role, if possible, of entrainment to the cues prior to the target. For this, we use data from 66 children. 40 of them are diagnosed with ASD between the ages of 6 to 9. They are doing 1 hour of experiment while being recorded with 64 EEG channels. The paradigm goes as follows. There are 2 conditions, the cue condition and the no cue condition. In the cue condition, they see 4 consecutive visual cues separated by an ISI of 650 milliseconds. After the last visual cue, they hear a tone. This tone is is their target, and they should respond to it with clicking a button. All these 5 stimuli appear in 1.5 hertz. So 4 visual, and then which are the cues, and 1 auditory target. The no cue condition is similar, but there is no visual cue that precede the auditory target. Behaviorally, we found a group effect. So overall, as can be seen here in those histograms, we see an overall slower reaction times for the ASD groups. When we look at the fastest responses, we can also see a cue effect. So both ASD and TD groups are faster whenever cues are presented prior to the target. However, we don't find any cue and group interaction. When we look at the VP across all 4 occurrences of the visual stimuli in the sequence, we also don't see any difference between the group. We can see here that the VEP is very similar, the visual evoked response is very similar between the TD and the ASD. However, when we unwrap the visual evoked response to the 4 stimuli in the sequence, we find something more interesting. We see a very similar response to the first visual cue. We still see it for the second. We see it for the third. But then we see something different between them for the fourth. What we see here is our first indication of altered anticipation processes. We see here a deflection in the voltage of the the voltage prior to the target, right after the 4th presentation of the cue. In the literature, this is called CNV, or contingent negative variation. It is a slow increase in scalp negativity. And it is observed when participant is expecting an impending stimulus and in rhythm-based predictions. So just to show you how delayed they are. This is, again, the same plot that I showed you before. While the TD group showed this CNV already 350 milliseconds prior to the target, the ASD group don't show it before 150 milliseconds prior to the target. So this is a difference of more than 200 milliseconds, which in terms of neuronal processes could be critical. So John mentioned before a delay of 30 or 40 milliseconds and how critical it could be. This is a delay of more than 200 milliseconds. It can also be seen here in those statistical T-maps. So what we see here for each electrode, the times in which the CNV effect was different between the group. And we can see it here again between 300 and 500 milliseconds after the 4th presentation of the cue. It is mostly seen in central and parietal sites. Okay, so we saw an indication of maybe altered anticipation process. But is there any difference in some process prior to this, like in longer time prior to the target? For this, I want to just show a little introduction on neural oscillations and phase. Neural oscillations reflect cycles of excitability with optimal phases for input processing and less optimal phases for input processing. So the efficiency with which a stimulus will perceive depends largely on the phase and the coherence on which it comes. So an event can be perceived non-optimally when it arrives in non-optimal phases, and it could be processed more efficiently if it comes in the high peak of the phase. So for this, to test entrainment, we took only a narrow band of the frequencies. We looked only at frequencies that are close to the frequency of presentation, which, to remind you, is 1.5 hertz. This is an overlay of the low-pass filtered signal on the not low-pass, on the wideband EEG signal. And what we see here is another indication of, is an indication of entrainment. We see that around the times of the stimulus of the cue onset here in the vertical dashed line, there is a much more dominant higher amplitudes of the black line represents the TD group than the ASD group. Statistically, when we measure those peaks for each individual in the group and then across the individuals per group, it was found to be significant. Another measurement that we could use is the degree of phase locking. So phase coherence, phase locking, is the degree of cross-trial phase coherence per frequency bin. So what we did here is for every frequency in the frequencies in the band of interest, we measured the phase for each trial and each individual. And then we did a measurement of coherence, again, per each individual. And just to give you some intuition, this is two representative examples. This is one TD subject, and this is one ASD subject. And you can see here, and each colored line is one trial. Okay, it's one EEG trial, low pass, just for this presentation. The black is the average. You can see how well those phases are aligned relatively to here. And believe me that these two examples are representative for their groups. So overall, we see a larger phase locking values for the TD compared with the ASD group. If we want to tie those findings to some speculatory explanation, I would say the following. It is known that there is a reduced interregional communication, both it was found both anatomically and physiologically in autism. It might be that abnormal communication, such as was found, caused to reduce synchronization in the system and to reduce phase locking, and in turn to reduce entrainment, and eventually, prior to the target, to reduce or delayed anticipatory processes of upcoming events in autism. Again, this is a speculation, and I wish to test and verify this. To conclude, studies suggest reduced anticipation processes in individuals with autism, but it is mostly based on clinical observation. But we show here objective indications to impaired preparatory mechanism in children with ASD. We show it through reduced CNV, altered entrainment, and reduced phase locking. I would like to thank everyone in the group, to Sophie, to John, to all postdocs, Ph.D. students, technicians, to the clinical core, and a special thanks to all the families and participants. John was missing from this year's picture, so I made some adjustments. Thank you.
Any questions?
Just had a quick question. How are you interpreting, it's a lovely paradigm, how are you interpreting the lack of a behavioral effect with the findings that you're seeing in the brain?
This is a great question, and we've been thinking a lot about this. So let me go back. Originally, this paradigm was designed to test other things, and it might be. So this is the first line here is the cue, and this is the target. The critical difference is way before the target, right? It might be that if this target would appear in this critical difference time window, we would have seen an altered behavior also. But this is, something that we think about only now. Yeah.
Just to tie it up, thank you, all of you who have stayed, for staying for all of the talks. It's been a pleasure to listen to everybody, and thank you to our speakers again. Very critically, I want to thank Lisa, Hillary, and Fran Andrade. They are in the front. You saw them when you came in. They did all the work, all the organization, and made this run as smoothly as it did. So we're very grateful. Finally, just a final thank you to all the speakers who came and made this a great day, and I hope you come and partake in some sushi and wine.